there's sigma bonds and pi bonds. A bond is an overlap of electrons, so the electrons that are being shared between two atoms. And the reason it's bonding is because the electrons are negative, the nucleus is positive, and so both of the nuclei are attracted to the same point, so they stick together. So the sigma bonds are going to be direct overlap along the axes between two atoms. So, for example, let's say I had two oxygen atoms. The one bond that they could form would be, there's this axis along them, so they would share their electron pair right there. So there'd be this overlap going between the two atoms. So I'm just drawing the overlap here, here, and this is an oxygen and another oxygen. So one of the bonds that an oxygen could form is sigma, and the symbol for sigma is a sigma. So there's sigma, direct overlap right in between the atoms. That's the most overlap you can get. And the second type would be, well, once there's this overlap right here, you can have what's a pi bond. A pi bond, same thing, I'll have two oxygens again. A pi bond is going to be outside the axes. So if this is the axis in between the two atoms, we could share a pair of electrons here. So these guys have to kind of have an overlap like that. All right, so they're still sharing the pair, but it's not directly in between. So that's the pi, and you can just draw a little pi. So the question would be, which one would be more stable, a pi bond or a sigma bond? And it makes sense that the direct, you're going to be able to have more overlap directly in between two atoms than indirectly. I would never pull a hand with somebody like that. That's bizarre. I wouldn't go over, I would go straight to that person. So the sigma bond is going to be the more stable bond, and it's because it's the direct overlap. You get more overlap. But if we're looking at that oxygen again, oxygen actually forms a double bond. So the first thing you do is you have your oxygens, they form that direct overlap right in between. So overlap, overlap, that's electrons spending time. The second thing you're going to do is, once you have that direct overlap, electrons are negative, so one pair of electrons repels another pair of electrons. So if I'm going to share another pair between these two oxygens, I'd have to put it somewhere away from this other pair, so it's outside of the axis, because inside the axis is already taken. So there's my pi bond. There's actually going to be bonding and anti-bonding underneath. So one pi bond actually has two lobes, but if you just remember, it's going to be outside of the axis. That's good. And once you have a double bond, if you're going to form a triple bond, so maybe I'll change this to nitrogen. So if I had nitrogen, which forms a triple bond, you'd have your direct overlap first. So from here and from here. Then you have your indirect pi, so something above and below. And then 180 degrees over here, we're going to have that anti-bonding lobe. The next thing you're going to have to do is form another pi bond, so another one that's going to be outside the axes. And since I already did top and bottom, I'm going to go to the right and to the left. So you'll have a bond that's directly in between two things, one bond that's going above and below, and then one bond that's going to the right and to the left. So imagine I could draw something coming straight out of the screen, which is not going to happen. It's just going to be nonsense. And then something going in the back there. So there'd be second overlap in the back. There we go. Oh yeah. Okay. So you have direct, indirect above and below, and indirect to the sides. And that would be how you form your triple bond. So to sum that up, if you have a single bond, you have one sigma, the most stable bond that you can form directly. If you have a double bond, you have one of those sigmas, the strongest, plus the second one, a pi, somewhere outside the axis. If you have a triple bond, then you have one of the strongest, plus one pi, and then a second pi, trying to get far away from each other. So you can see that the triple is going to be the strongest because it has the strong sigma plus the two weaks, where this double bond has the strong sigma in 1 week, and a single bond just has one sigma. And that makes sense. And also the strength of the bonds is going to bring them together, and having to get close together to have that overlap brings the two atoms close together too. So that's why the triples are shorter than the singles. What you need to be able to do for EP chemistry is just identify how many sigma and pi bonds is in something. So if you ever want to know, then you have to know if you have single bonds, double bonds. So we have to do Lewis dot structures. So this guy has 4 electrons. Each hydrogen has 1 valence electron, so 2. Every oxygen has 6 valence. I just count over on the periodic tables. There's 2 S's and 4 P's, so 6. So I'm going to have 12 valence electrons to work with. Carbon typically makes 4 bonds, so I like to put it in the center. I've got 12 electrons. I know I'm going to have to put a pair, and a pair to bond. So 2, 4, 6. This is good, this is good. This is not. So 2, 4, 6, 8, 10. Now oxygen isn't satisfied, and neither is carbon, so I'll make a double bond. Can't really tell it's a double. Yeah. So there's my double. And then if I'm going to fat eraser, there. Then if I'm going to figure out how many sigmas and pi's I have, well, the singles are 1 sigma, so I have 1, 2 sigmas. The double has 1 sigma, so there's a 3rd sigma. So this has 3 sigma bonds and just 1 pi because there's 1 double, and I know that I know that double has a sigma and a pi. Then here I have acetic acid, CH3COOH. So that guy is CH3C. It's going to be a carboxylic acid. There we go. Could count up valence electrons. I can also use the fact that I know hydrogens form 1 bond. Typically, carbons typically form 4. Oxygen typically forms 2. And I've seen the structure a lot. Okay, so I've got this guy. If I want to know the sigmas, I just count up 1, 2, 3, 4, 5, 6, 7. 7 sigmas. I just counted up anytime 2 atoms were attached because they're always going to form a sigma first. It's the strongest bond. And then there's only 1 double bond, so there's only 1 pi. And 1 more. The carbonate ion. So carbonate ion is CO3 with a 2 minus. So I've got 4 valence electrons here, plus oxygen is 6 apiece, 6 times 3. It's going to be 18. Plus a 2 minus charge, I'm going to have 2 extras. So I have 24 valence electrons. I'll put the carbon in the middle. I will first put 2 electrons bonding each of those, so 2, 4, 6. Carbon has 6 electrons, so I'm going to slowly satisfy each of the oxygens. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Now everything has 6 electrons, and I have 6 more to put on. Because I'm at 18, I have to go to 24. And I can see I've got 4 atoms that aren't satisfied, only 6 electrons to use. So I know I'm going to have to make a double bond. So there, that oxygen's fine, 2, 4, 6, 8, 2, 4, 6, 8. So now I'm at 22 electrons. Neither this carbon nor this oxygen are satisfied, so I'll do that. And this has a 2 minus charge, so I'll let people know. I put 2 extra electrons. And then I can say there's single, 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 3 sigmas, and there's 1 pi. So it's nice to know the type of bonding that's occurring, like how the electrons are being shared, and how that would affect the length of the bond, and the strength of the bond, so that 2 sigmas are stronger than 2 single bonds are stronger than 1 double bond, because you would have 2 sigmas versus a sigma and a pi. So it's good to know that, but for AP, we pretty much just count up how many sigmas, how many pi's.